little bit about some of the properties of the exponential functions. First of all, in here, the exponential function, we need, we need an inverse now. We have a log function. Now we're going to find the inverse. Turns out that this is going to be our choice for the inverse. And this will be true if and only if this is true. In other words, this will be our inverse if and only if this is the connection between x and y. Having this property will assure that we'll get these two results, which definitely means that they are inverses. So if you define your inverse function to the natural log as y equals e to the x, if and only if, in other words, they are inverses basically. Can't have this without that. Okay, so this is a condition on our function. So these two mean the same thing now. From now on, whenever we see y equals e to the x, it means the same as this. So we had no way of taking this function, switching the x and y, and solving it for the y. We had no way unless we define it this way. Okay, so, I mean, technically speaking, this is the inverse to this, okay? But we need a notation that is convenient for us, which would be this. Okay, so from now on, this means the same as this. Okay, although there's no real algebraic steps to take us here, we can assume these are the same. Okay, so now we have our inverse. And we've got a couple properties here. These are familiar properties to us. They can be proved using the natural log and then using the inverse. Here's some other properties. Domain for the e to the x, of course, is the range of the natural log of x, negative infinity to infinity. E of x is continuous, increasing, and 1 to 1. Of course, it's increasing because natural log is increasing. They would both have to be increasing, the inverse and its function. So natural log of x as well as e to the x are both increasing in 1 to 1. E to the x is concave up. That's not obvious. Okay, it's not obvious unless we found a couple derivatives, but we're gonna go with that for now. Concave up. And we also have a couple. I mean, if we just base it, if we know the natural log looks like this, then the inverse must reflect over that line y equals x. So you can see the concavity that in here that's concave up. And you can also see that the limit as x goes to infinity is infinity, and the limit as x goes to negative infinity is a 0. It must be if it's to be the inverse. So, okay, now, so there's a few properties, and now we're going to solve an equation or two. Okay, the exponent has our variable, so we need to get that out of the exponent. You do that by going to the other form, the inverse form, let's put it that way. So we can say this is the same thing as natural log 5 equals x plus 4. Okay, that's using, remember, y equals e to the x, same thing as natural log of y equals x. So that's essentially what we just did. Okay. Now, solving for x, we'll have natural log of 5 minus of 4 equals the x. So that's our answer for that one. Now, when we have a log equation, we use the exponential form to solve. So the equivalent exponential form looks this way. E to the 8 is 3x minus 4. Again, that's using this relationship here. To rewrite it and get to that argument, 3x minus 4. To help you go back and forth between these, it's often helpful to remember that the natural log actually equals the exponent. So, in other words, if the natural log is equal to the exponent, then when I use this form, I put that 8 in the exponent. And the base is the same as the base here, which is a base, we would call this a base E. Okay, so right now let's look at derivatives. Oh, wait, we didn't solve that one totally. We've got e to the 8 plus 4 over 3 is equal to x. Okay, let's do one more of these. Well, in fact, actually, let's hold off. We'll put that on our next video. This one's getting a little bit long.